Hello there, and a very warm welcome to Science for Sleep. Find a comfortable spot, let your shoulders relax, and allow the noise of the day to gently fade. This is your time, a quiet space where we wander slowly into some of the biggest questions in the universe, not in a race for an answer, but simply for the joy of the journey. This is a place where your curiosity gets to put its feet up. Here, science isn't a rigid set of facts, but a gentle, meandering river. It takes the long, scenic path, showing us the beautiful landscapes of thought along the way. There are no tests, no expectations, just the simple, peaceful pleasure of wondering. Tonight, our journey begins with something familiar: temperature. We know the gentle warmth of a sunbeam, the crisp chill of an autumn morning. We understand the heat of a campfire and the deep cold of a winter's night. But what happens when we travel far beyond these familiar sensations? We're going to sit with an idea that lies at the very edge of what is possible, a concept that feels almost too big to imagine, and is certainly too hot to touch. At its heart, temperature is simply a measure of motion. The atoms and particles that make up everything are in a constant, invisible dance. The faster they jiggle and vibrate, the hotter something is. The slower they move, the colder it becomes. We are heading towards a temperature so extreme, so utterly energetic, that our normal ideas about this dance, about heat, motion, and matter itself, begin to dissolve. To understand this ultimate high, let's first visit the ultimate low. You may have heard of absolute zero. It's the theoretical floor of temperature where particles have given up almost all their thermal energy. They become as still as they can possibly be, settling into a state of profound quiet. It's the cessation of the thermal dance, a state of minimum possible energy allowed by the laws of quantum mechanics. But now, let's travel in the other direction. Let's turn the dial up, past the heat of any furnace, past the core of our sun, past the fury of a supernova. At the very top end of the thermometer lies a ceiling, a theoretical limit just as mind-bending as absolute zero. It's known as the Planck temperature, or absolute hot. On paper, it measures around 2.55 times 10 to the 32nd degrees Fahrenheit. This isn't just hot. It's a temperature where physics as we know it, the very laws that govern space and time, cease to make sense. Take a moment to recall the warmest you've ever felt. Maybe you've stepped out of a cool car into the full force of a summer afternoon, feeling that wave of heat rise from the pavement, shimmering and alive. Or perhaps it's the familiar, comforting warmth of a bonfire on a cool evening, the radiant heat on your face as you watch the embers glow. It could even be the simple act of holding a hot mug, the heat seeping into your hands. These are the temperatures of our lives, the upper limits of our daily experience. These moments feel intense, a peak on our personal scale of sensation. But when we gently zoom out, placing our experience against the backdrop of the cosmos, they become vanishingly small. The surface of our own sun burns at thousands of degrees, its core a staggering 15 million. And that's just our local star. In the grand tapestry of the universe, these are but gentle embers. Our personal experience of hot is just the first, quietest note in a symphony of unimaginable energy. This channel is a quiet space for us to explore these immense ideas together, to find a sense of calm and wonder in the vastness. If you enjoy this gentle exploration through the strange and beautiful corners of science, I would be grateful if you considered leaving a like or subscribing to join our journey. It allows us to continue these meandering trips into the calm depths of the cosmos. So, where does this journey into heat end? Is there a final, ultimate temperature? This concept is known as absolute hot. To understand it, we must first remember what temperature truly is. It isn't a substance, but a measurement of motion. Imagine microscopic dust motes dancing in a sunbeam. Everything is made of particles doing a similar, constant, chaotic dance. The faster they jiggle and vibrate, the more energy they have, and the hotter we perceive the object to be. Absolute zero is the theoretical point where this dance stills completely. Absolute hot, then, is the opposite, the point where this dance becomes as frantic as the universe will allow. As we add more and more energy, these particles move faster. But there's a cosmic speed limit. Nothing can travel faster than light. As particles approach this ultimate velocity, their mass begins to increase, making it harder and harder to accelerate them further. Eventually, you reach a point where adding more energy makes the particle unimaginably massive and energetic. This theoretical maximum is the Planck temperature. It's a number so large it's almost meaningless. A 1 followed by 32 zeros. It's not just the hottest temperature we've measured. It is the temperature at which our understanding of reality itself breaks down. The very fabric of space and time would warp, and the laws of physics as we know them would dissolve into uncertainty. It is the veil at the edge of our knowledge, a humbling reminder of the universe's profound mysteries. Let's place absolute hot on a mental ladder of temperatures. A kitchen oven can hit 500 degrees. A candle flame burns at about 1,800. The surface of our own sun, our life-giving star, is about 10,000 degrees Fahrenheit. The core, where nuclear fusion happens, is around 27 million degrees. There are stars much hotter than ours, blue giants that can reach tens of millions of degrees in their cores. Supernova explosions can briefly push parts of space into the billions of degrees, forging the heavier elements we cherish, like gold and platinum. Collisions between neutron stars can briefly produce temperatures in the trillions of degrees. These forge elements that end up in our own bodies, and still, compared to absolute hot, these are cold. A trillion degrees is still roughly 30 trillion times cooler than the Planck temperature. The hottest we've achieved here on Earth comes from the Large Hadron Collider, creating tiny droplets of quark-gluon plasma at 7.2 trillion degrees. This recreates the state of matter from just microseconds after the Big Bang, when the universe was still unimaginably hot and dense. But at the Planck temperature, our two most successful and beautiful theories, quantum mechanics and general relativity, both demand attention at once. Scientists think the only time the cosmos was ever at this temperature was in its very earliest moment, lasting less than 10 to the negative 43 seconds. At that instant, all the forces we know, gravity, electromagnetism, nuclear forces, were unified in ways we can barely comprehend. Every single atom in your body, every molecule in the air, began in a universe that once burned at this unimaginable heat. At the theoretical limit of absolute hot, the universe as we know it begins to transform. Here, at what physicists call the Planck temperature, you've poured so much energy into such a tiny space that the particles themselves become secondary. The very fabric of space-time starts to react. We know from Einstein's famous insight that energy has mass. At these extremes, the sheer concentration of energy creates an immense gravitational pull on a microscopic scale. Imagine the universe not as an empty stage, but as a delicate, responsive surface. Each particle, supercharged with energy, becomes a heavy weight, pressing down, warping, and bending the reality around it. This is what makes the concept of absolute hot so profoundly fascinating. It represents the ultimate frontier, the point where our two greatest descriptions of reality, general relativity and quantum mechanics, cease to cooperate. General relativity describes gravity as the smooth, elegant curvature of space-time. Quantum mechanics sees the world as a shimmering, uncertain dance of discrete packets of energy. In our everyday world, these two theories live in separate domains. But at absolute hot, the immense gravity of the large scale is compressed into the tiny realm of the quantum. The smooth fabric of space-time meets the pixelated world of particles, and our physics simply stops. It's like trying to read a book where two beautiful but entirely different languages are written on top of each other. The meaning is there, but we no longer have the grammar to understand it. Within this theoretical inferno, strange new phenomena would emerge. The energy density could become so great that space-time might curve in on itself, pinching off to form what are known as Kugelblitzes, tiny, fleeting black holes made not from matter, but from pure, concentrated energy. These are not the monsters of science fiction. They would flicker into existence and, through a process known as Hawking radiation, evaporate almost instantly. Imagine a brief, silent shimmer of light, a cosmic spark that lives and dies in a fraction of a second. This constant creation and annihilation would fundamentally alter the rules, creating a chaotic foam where energy and space-time are locked in a fleeting, beautiful dance. And yet, in a strange and comforting way, this ultimate limit feels approachable. We can sit here, in the quiet of our own world, at our own comfortable temperatures, and let our minds wander to this edge of existence. It's a form of meditation, tracing the simple idea of hot all the way to the place where our understanding ends. It's a profound reminder that the most basic questions can lead us to the deepest puzzles in science. Every sensation of warmth we feel, from the sun on our skin to the coolness of a night breeze, is a distant echo of that first moment. The universe we inhabit, with its vast, cool emptiness and scattered points of light, is the direct result of cooling down from a state of pure, blinding energy at the very limits of what is possible.